In earlier presentations I showed how all signals are made up of sinusoids, but those sinusoids are of different amplitudes, frequencies and phases. In this presentation I'm going to show you how to use the FFT function in Matlab to analyze a discrete signal in order to determine the amplitudes, frequencies and phases of the sinusoids present in a signal. Now the FFT function can be used to analyze any discrete signal, but if in this example I'm going to use a very well-defined signal which has three sinusoids in it. So this signal x has three sinusoids. And the reason why I'm doing that is because if we know the sinusoids that are already in the signal, we can just verify that the FFT function works correctly. So in this case, the frequencies of the components are 20 Hz, 30 Hz and 40 Hz. So F1, F2 and F3, and there's my corresponding F1, F2 and F3. So the 20 Hz component has an amplitude of 3 and a phase shift of 0.2. The 30 Hz component has an amplitude of 1 and a phase shift of minus 0.3 radians, and the amplitude of the 40 Hz component has an amplitude of 2 and a phase shift of 2.4 radians. Now the length of the signal is that I'm going to analyze. Well, the length of the signal I'm going to analyze is 1.5 seconds long. Now I've subtracted a little bit off that length, and the reason for that won't be obvious, but hopefully by the time you fully understand the FFT function you'll appreciate why, but that will take some time. The sampling frequency is 1000, so if it's a length of 1.5 seconds, the signal should be 1500 samples long. So let's just plot x first of all. We'll just resize it. Okay, so there's my time domain signal, which results when I add the three sinusoids together. I got 1500 samples, and there's my amplitude axis here. Now using the FFT function is actually very simple. So I'm going to apply my FFT function. I'm going to create a new variable x. I'm going to use that capital X to store the frequency domain information associated with the time domain signal lowercase x. Now this is a very common convention to use, where lowercase symbols are used to store time domain information, whereas uppercase symbols are used to store frequency domain information. So what's going to happen is the FFT function will analyze the time domain signal x and store the result in the uppercase variable capital X. And when I hit return, all that work is done. All that's happened is the FFT function has been used to analyze x. Now the number of samples in x is 1500, so that time domain signal has 1500 samples. Now the new variable capital X also has 1500 values, but those values aren't samples. They're referred to as bin frequencies. So there's 1500 bin values stored in the variable capital X. And while X has lots of real values, so I'll just show you a few samples. I'll show you from sample number 2 to 10, or 2 to 6. All those values are real values for the lowercase signal. We've just created it. But the bin values are complex numbers. And I'm going to show you from bins number 30 up to, let's say, 34. Just show you a few samples, or a few bin values, just to show you. So there are, there's bins number 30. That's bin number 30. It's a value of 0 minus 0j. Bin number 31 is a non-zero value. Bin number 32 is also a zero value, as is bin number 33, and here's bin number 34. But you can see they're all complex values, and the complex values are used because they represent both magnitude and phase. Now remember that the FFT is trying to determine the magnitudes and phases of the sinusoids present in a signal. Now looking at the data like this is very difficult. It's difficult to interpret sequences of numbers like that. So it's more common to plot the magnitude spectrum or plot the frequency spectrum. But what we're going to focus in on is the magnitude spectrum first of all. So we're just going to look at the magnitude values associated with these complex numbers. So what I'm going to do now is just extract the magnitude data from the capital X value, which is a set of complex numbers. and I'll just hit return. That ABS function is a built-in function in Matlab to determine the magnitude values of complex numbers. We'll take a look at the 30 bins number 30 up to 34 again, but this time we're just going to look at the magnitude values and we relate it to the complex numbers up here. So the magnitude of bin number 30 is a value of 0, and that's the corresponding complex number. The magnitude of bin number 31 is a value of 2.25 multiplied by 1000, so that's 2250, and that corresponds to this complex number. And you can see that the rest of the complex numbers are 0, so therefore their magnitudes are 0. Now what I'll do now is just plot the entire magnitude spectrum, as it's called. So Xmag is my entire magnitude spectrum, and there is the magnitude spectrum. You can see that there's values of 0 up to 1500. These are the frequency bins. Okay. Now this range of values between 0 and 1500, that will vary depending on the length of the signal. The time domain signal that I created had 1500 samples, and that's why I have 1500 bins as well. Now you'll notice that on the left hand side here I have 3 spikes. Okay, each of those spikes corresponds to a frequency component. Or in other words, they correspond to sinusoidal components. Now on the left hand side I have the 3 components, but I also have another set of 3 components on the right. Now what you should notice is that the right hand side components are a mirror image of the left hand side components, and this is going to be the case anytime you plot the magnitude spectrum. Well, I'll put a caveat on that for signals that you're going to deal with, and the signals you're going to deal with are real signals. So just for the moment, just accept that anytime you plot the magnitude spectrum, we really just need to focus in on the left hand side of the magnitude spectrum. So I'm just going to zoom in on the left hand side because the right hand side information is effectively redundant. Okay, so there's the left hand side of the magnitude spectrum. I am just going to put a few labels on this. This is my frequency axis, and this is my magnitude axis. Now the frequency axis isn't in hertz, it's in bins. Okay, and that's just a term that you need to get used to, the same way as in the time domain you're dealing with samples. In frequency domain you're dealing with bins. So this isn't written in here, but I'll just put 750 there because halfway up is 750. Now frequency in bins can be easily converted into frequency in hertz, and the rule is actually quite straightforward. This here, halfway up, in this case 750, is always corresponds to half the sampling frequency. Now in our case the sampling frequency was 1000 hertz. There's 1000 hertz. That means that this frequency is 500 hertz. Now it's important that you remember that no matter what number of numbers appear in terms of bins, so if there was 1,000,000 bins and halfway up was 500,000, well then that 500,000 would still correspond to half the sampling frequency. So I might just make a note here. This is always fs over 2, this point. That means that halfway down along here, around this point here, it's about halfway down, that would correspond to 250 hertz. And halfway down again, which is roughly around there somewhere, that'll be 125 hertz, and this point here would be roughly 60 hertz. Now you can see that all these 3 components lie between about 10 hertz and 60 hertz, and if you recall, when I created the signal, the 3 sinusoids that the 3 sinusoids in the signal that we created were frequencies 30 or 20 hertz, 30 hertz and 40 hertz. Now let's take another look at this. Oh, my pen has gone. I might just try to restart that. Sorry, a bit of a problem there. Just give me 1 second. I'm just going to reset something and I'll start it up again. It's just the pen application that I'm using needs to be restarted every so often. So I'm just going to click OK. Now my pen should be back. Okay. So we had identified that this halfway up point of 750 bins corresponds to 500 hertz. And we'd also said that this point here was about 60 Hertz. And this was frequency, and this was magnitude. Now, looking at these, we see there's three components. And what we can say is the amplitude of this component looks like it's about 1500. This one here looks about half that amplitude. So this one here looks at about 750, whereas this one here looks like it's 1.5 times that. So that's about 2200 up there. Okay, so analysing that signal a little bit further, what I could say is that there's three frequencies present. We call that F low for the lowest frequency component, or the lowest sinusoid. This one here, we call it FM, the middle frequency, and we'll label this one as F high. And what I could say is that the middle frequency component is half the amplitude of the highest one, and 1/3 of the amplitude of the lower one. So if I was just looking at this signal in the frequency domain, I knew nothing about the signal, what I would be saying is that there are three sinusoids present. The amplitude of the middle one is 1/3 of the amplitude of the lower one, and half the amplitude of the higher one. Okay. What I'd also say is that there is no frequencies present for all other frequencies, and the reason I say that is because the amplitude of all these frequencies down here, following that blue line there, are all 0. So that tells me that there's no sinusoids in that frequency range. Okay, and that's basically how you analyze the magnitude spectrum of a signal using the FFT. The most difficult thing is actually getting the scale of the frequency axis right and being able to flip between bin number and frequency in hertz. Now let's just quit that and go back into the time domain representation of the signal. So I'm just going to plot it out, or write it out here again. Now we can see that the lowest frequency, here's the lowest frequency, is a frequency, we know that, well, I'll just write it out again. F1 is 20, F2 is 30, and F3 is 40. We can see that the lowest frequency is 3 times the 20 Hertz or the 30 Hertz component. Okay, 3 times that one. That middle one is an amplitude of 1, whereas the other one, the lowest frequency, is an amplitude of 2, or sorry, an amplitude of 3. The higher frequency is an amplitude of 2, which is twice the middle frequency, which is what we saw in this magnitude spectrum. Okay, so straight away we can see how the magnitude spectrum is used to identify the presence of sinusoids. Now, the next piece of information that you just need to get used to is to get the angle or phase information from the magnitude spectrum, or not from the magnitude spectrum, but from the magnitude information which we've stored in that variable called x. What we're going to do is create another variable called x phase, and that's going to be equal to the angle of capital X. And this is very similar to the absolute function, except instead of getting the magnitude, it gets the phase information from x, which, if you remember, is a set of complex numbers. Okay, now what I'm going to do now is try to find the phase values of the three components. So I'm just going to open up the magnitude spectrum again and try to find the bin number. So here's the bin number here of one of the components. Hold on, I'll do that again, just slower, so you can see what I'm doing. What I want to find is the phase values of each of these bins. So I'm just going to zoom in on this one here to find out the bin number. So the bin number of that one is 31. See that there? That's number 31. Let's get the corresponding phase of that. I just need to type x phase 31. And we see we get a value of 0.2. I'm going to zoom in the other two peaks now just to see what their bin numbers are. So let's just zoom out a bit. I'll zoom in on this smaller bin, and it's got a bin number of 46. So the phase value of 46 minus 0.3, and I'll zoom out on the magnitude spectrum again. Let's zoom in on the third peak. Let's do that. So there's the third peak. Let's zoom in on it. Its bin number is 61. So let's get the phase value associated with that. 61. So 2.4. So let's remind ourselves what x is again, and we can see that the phase value of the third or the highest frequency component is 2.4, which matches this. The phase value of the middle frequency component is minus 0.3, which you can see here, and the phase value of the lowest frequency component is 0.2. We can see that matches. So basically what I've shown you is that the FFT can be used to extract the phase information from the signal. I've also shown you in the magnitude spectrum, here's the magnitude spectrum again. Magnitude spectrum is used to show you the relative phase or the relative amplitudes of the various components. And generally that's all you're really interested in. You want to be able to say, well, where's the spectral energy lie in a signal? So in this case, for example, the spectral energy lies in the low frequency region. And we could actually say there's spectral energy between 10 Hz and 60 Hz and no spectral energy outside of that range. So they're the general observations you make when you look at signals in the frequency domain. Now I could get the absolute values of these, but it's not really that important. I'll show you how to do it, but I wouldn't be overly worried about doing this. If I wanted to get the absolute values of those signals, I could divide by the FFT len, or half the FFT len, sorry, which in this case is 750. So if I divide all the magnitude values by 750, I'll get the absolute magnitude values. So there, I've just done it. I've plotted the magnitude spectrum. I've scaled the amplitude axis, and you can see that the lowest frequency now has a value of 3. The middle frequency has a value of 1, and the highest frequency is a value of 2, which corresponds to the time domain signal that we created. Okay, so that's a quick overview of how to use the FFT function. There's plenty more to it. This is kind of a simplified view, and I'll try to put together a few more demonstrations to show you how to do it. Anyway, thanks for your attention.